Hope all of us are doing great. My name is Ernest, and this is Ernest Sciences and Mathematics TV channel. In this particular discussion, we're going to look at another concept under the concept of quantum mechanics, and this basically is the concept of a particle in a box. Now, in this specific discussion, this is going to create for us a basis of trying to evaluate molecular problems from this specific approach. And the particle in a box is going to be an hypothetical illustration, of course, which is going to assist us have various ways of illustrating the quantum mechanical principles. And in some cases, we're going to see that from the Schrodinger's wave equation, of course, we're going to find some ways in which we will solve some of these specific problems, which are resulting from the Schrodinger's equation. And of course, in some part of our discussion, this specific concept of a particle in a box will give us a colon describing the discrete energy levels, which of course are going to arise from this specific description of a particle in a particular volume in space. Now, therefore, I'm going to use the illustration that I've got, or rather the one that I've written on the right side of my board. That is going to form, of course, a basis for us understanding this whole aspect of the simple quantum or the simple systems in quantum mechanics as I've illustrated. So in this case, basically, a particle in a box is going to constitute these two specific boundaries that I've given. And these are going to form what I refer to as walls. So in this case, this particular case for the range of course, the space between x is equivalent to 0 and x is equivalent to L. So basically, this is going to define the length of this particular box, and the two walls are going to be infinite walls, which are going to be given in terms of this specific representation. And then therefore the potential inside this particular box is going to be 0, but the potential outside this particular box, or the region which we are going to refer to as a restricted region, is going to be infinite. So therefore the box, the region inside this particular box is the region that we consider to be the region whereby this particular electron is going to be located. So therefore, for us to evaluate this specific situation, we're going to create some boundary conditions whereby, as I've said, we're going to restrict the value of x within this specific region. So we're going to have perhaps a piecewise defined function for having these specific values between 0 and infinity for the two walls. And this is going to be given in terms of x, which is greater than 0 but smaller than L in the first case. And for this infinite condition, we're going to have x equivalent to or smaller than 0. And then we're going to have as well x greater than or equivalent to L given as such. And this is going to show the restricted area for this specific case for x. So for x equivalent or smaller than 0, it's going to imply, of course, this particular extension towards my left. And then we're going to have x greater than this specific region is going to imply a region of infinite potential, which is outside the box in that particular case. So for us to evaluate this one, which is a description of the particle in a box, we're going to employ the concept of Schrodinger's equation, which is going to describe the motion of an electron in a one-dimension box. And of course, this is going to be given in terms of d squared, this wave function dx squared given as such. And then we're going to have this one given in terms of 8 pi squared m all over h squared given as such. And of course, we said that whenever we're going to use this specific concept, we're going to have the difference in energy given in terms of energy minus the potential energy of this specific wave function is equivalent to 0 given as such. So in this case, if we consider this particular wave function, I'm going to assume that we are fully aware of the full representation of the Schrodinger's equation for a three-dimension coordinate system or a coordinate or a three-dimension which has an element of volume, whereby we have this specific representation for a change. So this is a Laplacian operator which is going to have a change in x, a change in y, and then a change in z given as such. So we're going to use this element of volume over x for this specific particle which is restricted within the x-axis given as such. and this is going to give us a version of the Schrodinger's equation from that specific representation. So considering the case of a potential which is equivalent to 0, so therefore this particular equation is going to be given in terms of d, the wave function dx, and then we're going to have 8 pi squared m over h. So this h squared, and then we're going to have this e, this wave function given in terms of this specific representation giving us x. So basically we're going to have this potential given as 0, and that is going to represent that equation for that specific particle. Now in this case we can have this version of a different version of this specific second equation, whereby we are going to substitute a particular part of the equation with of course a constant which is the square of k, and that is going to give us k u represented as such, and then this is going to be this specific value having this particular representation. So I'm going to have this k implying this particular portion of the equation, and therefore from this we're going to have the value of k, the square of k represented as 8 pi m all over h squared given as such. But we have seen that from our previous discussion we can give the equivalence of the h over 2 pi given in terms of a h with a heart or a stroke given as such. So implying this specific part of the equation can be reduced into a form of so there's a e which are basically not written. So this is equivalent to a version of the equation which is a 2m e all over this representation of h squared, and this basically represents this particular aspect of the square over k, which we are going to use later in our discussion. Now we can find a solution to this specific representation of the Schrodinger's equation of a one-dimension box by using the concept of the function of a wave. And of course I'm going to use the general representation of a function of a wave given in terms of this wave function is equivalent to a, the sine over kx, plus b, the cosine over kx given as such. So this is a general representation for the solution of this specific version of the Schrodinger's equation for one dimension, of course, which we are representing in form of a box. And in this case, for us to find the solutions for this, we are going to say that a, b, and k are going to constitute a non-constant, and therefore that calls for us to create this, or to use this state of these two specific boundary conditions which we have created, whereby the first case we're going to see that whenever x is equivalent to 0, the value for the function over x is going to be given as 0, and the absolute value of this specific function as well is going to be given as 0. So that's our first condition that we're going to create. And then next we're going to have a condition whereby if x is equivalent to L, the value for this wave function as well is going to be given in terms of 0. And then we have to have the square of this wave function as well represented as these two specific points. So at these boundaries, the value of this function is equivalent to 0. And this, of course, is going to cater for the issue of discontinuity that we're going to look at later in our discussion. So therefore, we can consider this specific general case for representation of this wave function and try to do a substitution for the first and second condition and see what kind of an equation we're going to come up with. And that is going to represent the general case for these specific values of perhaps the energies that we're going to see later. So in this case, if we have this first boundary condition, we're going to have this value for the wave function, as we say, be represented by 0, and that is equivalent to a, the sine over kx. And this value of x, as I said, is 0. Therefore, we're going to have that one given as such, and b, the cosine over k, at 0 given as such. So in this case, this is going to give us the value of 0 is equivalent to 0 plus b. And this, of course, as we said, this specific value for the cosine of this 0 is going to be 1. So therefore, we're going to have the value of B given as 0. So in substituting this specific value in this particular case, we're going to have the second condition of this specific wave function given in terms of the value of 0 is equivalent to A and the sine of k. And then we have said that this specific value for x is equivalent to L, unlike the first condition where it was equivalent to 0. So this is going to be equivalent to KL given as such. And we have said the value of B from the first condition is equivalent to 0. So this gives us a general equation of the form of 0 is equivalent to A, the sine of KL. And in this case, we had said that we can have this specific value for A, which is basically for the particle to be existing within this specific box, or for the probability of a particle to be found within this specific box. The function of A is not equivalent to 0. Therefore, for us to satisfy the condition for this particular equation, therefore, the second aspect of the sine of KL, then therefore, is the part which is going to give us this particular value of 0 given as such. And from a description of the graphical representation of trigonometric functions, we're going to see that this specific value is going to be true for values of n pi. Therefore, for the value of this particular function of the KL for the sine, whereby the value is 0, these are going to be satisfied by n pi given as such. And therefore, we're going to have this specific representation given in terms of KL is equivalent to n pi given as such. So implying the value for k is equivalent to n pi over L given as such. So therefore, this is going to give us a general representation of an equation, which is going to represent the probability of this particular particle in a one-dimension box given in terms of the sine function. So therefore, we're going to consider this specific case. And decide that basically for this, we're going to have a substitution for the value of k, whereby we had said that k basically is equivalent to n over n pi over L in that specific order. So I'm going to do away with this. Hope that we are following this specific procedure. So we're going to have the representation of this specific function given in terms of a, the sine of. So k is equivalent to n pi over L, but this particular function for the sine has got x given as such. So this is going to be the general representation of the equation, or rather the function representing the set of this specific particle in a one-dimension box given as such. Now, in our subsequent videos, we're going to look at the various ways in which we can obtain the exact probability by doing the normalization of this specific function, and we're going to see what form of the equation we're going to come up with that is going to represent basically the probability of finding a box in a one-dimension, or perhaps in the xy plane, and in the using the volume element in space, and that is going to give us a three-dimension state for this specific particle respectively. So I hope that this concept of a particle in a box is going to open for us a window of understanding the various aspects of the description of a particle in a box, and that of course is going to give us a clue for explaining the existence of an electron around the nucleus using the Schrodinger's equation that we had mentioned earlier. So that is it for now, guys. Bye, God bless you. Catch us in our next video.